Jason Newby was born in McMinnville, Tennessee, went to King College in Bristol, majoring in physics and math, then came here to the University of Tennessee for his PhD in physics, specifically high energy nuclear physics. He then went to Lawrence Livermore National Laboratory, a very distinguished place. And in 2009, Oak Ridge National Laboratory, knowing a very good thing when they saw it, grabbed him, brought him back here, and he has been here. When he was at Lawrence Livermore, he won awards for research. When he was here at Oak Ridge, he has won an award for research. He has, this boggles my mind, about 200 published articles in scientific journals. Now think about that, because this is a young man. He is publishing articles at the rate of about 10 a year. I've made a lot of these introductions. I cannot remember anyone who has even remotely approached that publication record. So we're very fortunate indeed to have with us today Dr. Jason Newby talking about neutrinos, exploring the universe with nature's ghost particles.
I may be blushing a bit for that very warm and generous introduction. Thank you all for coming. Thank you all for your interest in this topic, and I hope I reward that sufficiently. Regarding those publications, there are part of my experience here at the university was working with a great advisor, Soren Sorensen, who did a rotation as chair of that physics department. And I was part of a large community of research at the Brookhaven National Laboratory doing relativistic heavy ion physics. It's a collaboration of about 500. And I've read all of those, but I did not write all of those in person. But the system, that's the way that they award it or credit it. And so I've been fortunate in that regard, but also been fortunate in that environment to work with a lot of really great people. And so I've had a great transition in the last 5 years from one very exotic form of matter. And at Brookhaven, we would collide golden nuclei at relativistic speeds almost the speed of light. And when they collide head on, they would produce such a dense form of matter that had not existed really naturally since early stages of the Big Bang, and with all sorts of implications for gravity analogs and evaporating black holes, and then some nuts and bolts physics. As I look around the room, how many of you are particle physicists here at the lab? Okay, and then there are a few physicists, I think. So I need to know who to look for when they shake their head. I'm getting something wrong. Anyway, so about 5 years ago, I made a transition from one area of physics to another, and I love it because it's always nice to discover something new. And it's always nice to join a field and work with a group of people, especially young people, where there's a lot of energy. And I've really enjoyed working with students who usually know more about these topics than I do. And so in this excitement, I'd like to share that with you today. All right? Okay, so first thing, when I began looking at neutrinos, I had no idea from my RIC education, relativistic heavy ion field, that neutrinos were just as ubiquitous as they are. All right? So neutrinos are literally everywhere. In fact, most of the most prominent natural source is from the sun. There are 60 billion traveling through your fingernail every second. And the second maybe is something like the radiation from the radioactive decay of natural elements in the Earth. Those are something that are producing neutrinos. Cosmic showers where, out in the solar system, these high energy protons interact in the upper atmosphere. They create these massive showers. Part of that shower includes neutrinos. There are even relics from the Big Bang. Some of you may have heard of the cosmic microwave background. That is when the light suddenly became, the universe became transparent to light. And that afterglow is present today. I'll say a few words about that. It turns out neutrinos have an analog to that we have yet to observe, but it's kind of exciting. And you're familiar with nuclear reactors. First observations of neutrinos were actually made at nuclear reactors. There are some even more rare cosmic events, like supernova, that I think I'm just fascinated by how complex a system for a type 2 core collapse supernova, and I'll spend a little time talking about that. And just this year, there was a first observation of a multi-messenger ice cube, is a neutrino experiment, and they observed just a neutrino of energy scales that we don't explore even in accelerator laboratories. It just that was later correlated with a traditional observational signals. Okay, so before we dive into this, I just need to warm up a little bit on scales, and so let's camp here for just a minute, and go from our natural world that our brain is ready to process down into the particle level. And I'll start with the view of a 1 meter scene, a field of flowers, and then I'll zoom in a factor of 10 each time in a sequence, and you can see in this 1 meter frame there's a flower, and on that flower is a bee, and then we then zoom in on the bee's head, the bee's eyes, and on that bee's eye was a piece of pollen. And then if you look at the pollen, there was a bacterium. And then on the bacterium, we have a virus, right? And then on that virus, you can see the DNA that makes up that virus. And ultimately, that virus is made up of atoms, carbon, nitrogen, oxygen, hydrogen atoms. And so we've now gone down from a meter scale, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 9 zeros being added to the 1 in 10 to the 9th scale of a meter, right? So it's enormous scales. Now, an atom was 1/10 of that, right? So 10 to the minus 10. And so it's at this scale that we can start talking about particle physics. We have in the nucleus of an atom protons and neutrons. The protons are positive charged, neutrons are neutral. That's convenient for naming. And then we have the electrons, right? Now, this is 10 to the minus 10th, but we never quite give this picture quite right. And if you were to so a question for you, if an atom is the size of the UTK campus, I'll say roughly a kilometer in radius on this picture. So what's the size of the atomic nucleus in everyday units? Any guess?
Baseball?
Baseball, close? Yeah, nuclear, it's actually about a centimeter, okay? Right. And this becomes, so those electrons that are orbiting in that picture really are very diffuse, right? They take up a whole lot of space, but the nucleus was just this 1 centimeter core at the center, and that'll become important later. All right, so to talk about neutrinos, we have to go one level deeper, and so we're going to deconstruct the universe to its fundamental particles. And it turns out that's not quite neutrons and protons, although at one scale they suffice. Actually, neutrons and protons are made up of smaller particles. And so what's shown here is the standard model of elementary particles and their interactions. And so we have protons and neutrons actually being made up of smaller particles called quarks. There are 3 generations of these. The familiar electrons are in another family of particles called leptons. And suffice it to say that most of our experience, we can sort of ignore some of these others. And so just for simplicity, I'll focus on those. So these up and down quarks then, in different combinations, then make up neutrons and protons. They come in 3. And then there are a series of force carriers. We call those bosons. And those act as mediators of various forces for which these fundamental particles will interact. And so the strong force is mediated by the gluon. And so the up and down quarks carry a charge, a color charge, we call it, that's mediated by that strong force. And it's really that force that holds those quarks within the proton and the neutron. Electric force, well, the up and down, they have a positive 2/3 for the up, a minus 1/3 for the down. And so in various combinations, you see how you can assemble those to have a +1 charge for the proton, and neutral then for the neutron. The electric force, the electron, as you know, also has an electric charge of -1. And then neutrinos are kind of the oddball in this. They don't have either of these charges, but they have something called a weak charge. And they interact via these force carriers. Okay? But the neutrinos do not interact. They don't have an electric charge. They don't respond to the strong force. And so we call that force a weak force, and I'll illustrate partly why. And this is important to get kind of to camp on for a little while, because in this diagram then is how neutrinos that are so ubiquitous, as I mentioned, come about, right? And so it's all about the way that we see neutrinos is in some form of converting one of these ups to a down or a down to an up. And so this diagram shows in time you've got 3 quarks. There's some process by which you can convert those to an electron. And because within a family you have to conserve lepton number, it's one of those conservation laws, just like conservation of energy, conservation of mass, conservation of lepton number, you need the anti-lepton, in this case it's going to be a neutrino, to kind of do all the bookkeeping and balance the books. All right? And so a lot of the processes we're talking about really are one permutation of this. You're either converting an up to a down or down to an up. You're either emitting an electron and antineutrino, or in some cases absorbing the neutrino in the process of doing that conversion. And really, everything, all of these processes, that'll be one of the most fundamental interactions. So I said it was weak. And so how weakly interacting really are they? And so I think the easiest way to do this is consider how much lead. That's one of the heaviest things we can get our hands on. We all know it's very effective at stopping things. How much lead would it take to stop various particles? If you're just talking about visible light, it's 10 thousandths of an, or 100 thousandths of a centimeter. X-rays. If I had dental X-rays, you know, they put that blanket on you for you to limit the X-ray exposure to just, you know, your teeth. They put that blanket on you. You need about half a centimeter to stop that. If you have higher energy electrons, you need a full centimeter. Energetic protons, much as 30 centimeters. But for neutrinos, we're talking about a billion centimeters of lead to have the same effective stopping of those neutrinos. Okay? Now that's the approximate distance from our sun to the nearest star, right? And I think that when I've asked some of the Rafe Hicks and others, I think there are estimates that there's not even that much lead in the universe, right? So neutrinos really are very weakly interacting. So then that begs the question, if we'd like to use neutrinos at all, or learn anything from them, or use them as a tool, how can they possibly be useful? And the key is in the fact that that weak interaction is both a curse and a blessing, right? The curse is that for you to know that it was there, you had to interact with it. So that's going to be hard. They're going to be difficult to detect. But it means that if you're interested in something, a process that is inaccessible from almost any other means, neutrinos are still going to get out, right? And so the second issue is there are plenty of processes that are producing copious numbers. So you combine these copious numbers, right? I said 60 billion, right, into your fingernail every second. Then these copious numbers with large detectors, right? Moles of atoms, each with the potential to interact. And for example, every human actually is emitting 300 million a day just from the food you eat and the radioisotopes you ingest naturally, potassium in bananas and so forth. Okay, so can they be useful? And I'm trying to convince you that they can. And I think the first kind of fun example that I'll come on is to settle an old score. When Darwin was working through his Origin of the Species, Lord Kelvin said, no way, there's no way that's going to work. You need too much time. The Earth's not even that old. And Kelvin had this argument. All the chemical reactions, you're at best going to get 20,000 years out of the sun. Gravitational energy, maybe a few million years, but you need a lot more time than that. And you would need basically a 50th of the Earth falling into the sun every year to get the gravitational energy to sustain the sun. There's nothing on the books that could do that. In fact, he said, unless sources now unknown to us prepared in the great storehouse of creation, we can say with certainty that inhabitants of the Earth will not continue to enjoy the light and heat essential to their life. I mean, this was such a compelling argument that Darwin removed a lot of that language about discussion of the timescales from his final draft. So, the great storehouse of creation then, that Kelvin didn't know about, Einstein provided a pathway for this, and that is what once was thought as conservation of energy and separately conservation of mass. Einstein said no, actually they have this relationship. The energy is actually equal to the mass. The c is the speed of light. That's 3 times 10 to the 8th. So square it, it's an even bigger number. There's a lot of energy in mass that can be converted. And for a simple example of how that works, you take a neutron. A neutron on its own is not very stable. It will decay in 15 minutes or so. And what it does is it decays to a proton and an electron. And if you add up the mass there, the proton and electron don't actually make up for the entire mass of the neutron. So some fraction of that gets converted to energy. Okay? Now, this is an enormous amount of energy that can be tapped. Certainly the Manhattan Project was one attempt to harness that energy. An additional thing is when they did the bookkeeping here, they actually didn't add up to the total energy between the electron and the proton and the neutron. There was more energy missing. And Wolfgang Pauli is the one who posited that there could be a different particle that we've never seen before. It would have to be really small in mass, and it would have to be really weakly interacting. But he knew that something was carrying away this extra information. That was such a wild idea at the time. When they submitted it to Nature, Nature rejected it. And so it was only some years that the first publication didn't go to Nature but went to Science. It was published there. All right, so in the 30s, Hans Bethe and Carl von Weizsäcker, they had worked out an idea first proposed by Arthur Eddington that this could be the mechanism that fuels fusion in the sun. And so in this process, the simplest of the processes, you end up with hydrogen, that is 2 protons, through this cycle, ending up forming and burning helium. Okay? And in the process, there are several stages where you end up with neutrinos. But you also end up with some gammas or some light being emitted. And that light and that energy can then go into fueling the sun. Now, the total amount of hydrogen that it would take then to produce this effect is 600 billion kilograms per second. So it's converting 4 4.3 billion kilograms per second is the total amount of mass being converted to provide that energy. But the sun is really, really big, right? So we've got another 5 billion years, and so we're okay. Now, this seems to work out in the math, but how do we know that? How do we know that that mechanism really is what's going on in the sun? And Raymond Davis came up with this idea. He said, if those neutrinos, it takes forever for the photons to get out. But that's okay. All the information will be washed out. But the neutrinos, they're getting out. And we should go look for those. And he knew that those would be electron neutrinos. And he knew that chlorine atom, when the electron neutrino interact with chlorine, a certain isotope, it would produce argon-37, which isn't stable, and that might be detectable. And so what he did is he put 100,000 gallons of dry cleaning fluid, right, into a big container, and then put it deep in the underground mine, and waited for these chlorine atoms to be converted to argon. Now, there was no really practical way to detect it, and so what he was going to do, I think this is just ingenious, he would bubble helium every week or so up through this vat of dry cleaning fluid, and all the argon would then attach to the helium gas, and then he would collect that helium gas, put that in a chamber that he could count. Now, the rate he's expecting for this is on average 1 a day. So he designed an experiment where he thought the rate would be 1 a day, and to see that 1 a day, he was going to have to count 1 atom in 100,000 gallons of fluid. That's hubris, right? But it worked out. And he confirmed that there is indeed a thermonuclear reaction inside the sun by counting those atoms, and he was rewarded with the Nobel Prize, not some years after he originally made that observation in 2002. Now, there was a large caveat to that. So that was a huge success. The large caveat was, actually, he didn't see all of them. He only saw a third of what they expected. All right? That meant that either there was an error in his experiment or the theory of the sun was wrong. And so people kept accusing one or the other of that. And it turns out, actually, neither was true. It just meant that we didn't understand the nature of neutrinos. And so it was proposed then in 1957 that neutrinos are this weird kind of particle that they could actually oscillate from one flavor to another. And I told you didn't have to worry about those other generations. Remember I covered those up? Well, that's not quite true. In this case, the neutrinos, the electron neutrino that's kind of the lowest mass, the one most tightly coupled to the electron that we know and love, well, it can oscillate to this muon flavor or this tau flavor. And so what was happening as they were coming from the sun, they were oscillating to one of these other flavors that chlorine didn't react with. All right, and so it wasn't until 2001 that a neutrino observatory, kiloton scale of heavy water, where you're looking for interactions on deuteron, it found those missing neutrinos using an interaction that was sensitive to all 3 flavors. And so we learned in the process of trying to use neutrinos as a tool, right, to investigate, we also created a puzzle that taught us something about the nature of these particles themselves. All right, another fun story is about the evolution of a massive star. And this is another environment, very inhospitable. You can't see inside an active star. If you have a large star, say 25 solar masses, it goes through a sequence of burning first the hydrogen into helium, and then subsequently heavier and heavier elements until it's burning silicon. And it builds up this sort of onion structure. But at some point, you've got iron. Iron doesn't have a process to fuse to go to a heavier element. And so once you get this iron ash in the center, it starts to cool, and as it cools, there's not enough energy to push against this enormous gravitational force, right? And so because it can't push it against that, the pressure eventually is so great that the iron is ripped apart, and it becomes favorable for individual protons to capture the electrons. Remember those electrons that were so greedy with space, right? 10 to the 5 or so. You know, those are captured, and so when a proton captures an electron, you end up with a neutron. Those neutrons just form one big ball, like one big nucleus, right? So all that empty space, it's like pulling the rug out from underneath, gravitationally speaking, the rest of the star. And so all this mass starts falling inward, enormous amount of gravitational energy is produced, and suddenly that mass hits the outer boundary of the neutron star, and a shock wave comes out, right? Now, it's that shock wave, that really very unique environment, very dense, that's where a lot of the heaviest of elements are created, higher than iron. And so the reason we see those is because somehow that material got ejected from that core collapse supernova. They tried to make simulations that could reproduce this. They kept getting it wrong. It wouldn't blow up. Turns out the neutrinos that are produced in that neutron star, they don't interact a lot, but there are so many of them, and when they do interact, it's enough to just push that shock wave along, and that's how we get the dispersing of those heavier elements, because neutrinos are giving that shock wave the little extra boost it needs to overcome the stalling as it dumps all its energy in this nuclear cooker. Now, in that brief moment, there's a flash of light that's brighter than 100 billion stars, brighter than the whole galaxy that it rests in. However, only 1% of that total energy comes out as light. 99% are neutrinos coming out of that system. And so I've described a process. It's really complicated. They run these simulations on enormous computers to try to get this right. So it's a nice idea, but how do we know that that's really the correct description of the core collapse supernova? Well, in 1987, the only modern day nearby supernova, we saw this massive flash of light outshining the rest of the galaxy. And there were 3 large neutrino detectors, kiloton scale neutrino detectors that were designed to do completely different physics. And they saw a burst of neutrinos. First, one wave, and it only lasts about 13 seconds. Okay? But these are 3 experiments seeing 3 independent observations of these neutrinos all bunched up. And it arrives before the light. And so, and then it arrives in these 2 stages. And it turns out that's largely aligns with the theoretical description of the way that a type 2 supernova evolves. And so they are building 10 kiloton scale detectors for different purposes, but now they want to be ready on the 100-year time scale when the next similar supernova observes, that they have detectors ready to take high fidelity data that could measure this time profile so that they can see inside these supernova stars to validate that theory. I have one other example. It's about the Earth. We actually have a similar problem that we can't see inside the Earth. You can only go about 12 kilometers, about as deep as I think you can drill down. And we actually don't know we've never proven what's actually measuring or what's producing the heat within the Earth. And we've measured the output of the heat. We know that you can do cores, measure the temperature difference along the path length and the thermal conductivity. And we know that it's producing about 46 terawatts. 46 terawatts, that's like 46,000 watts bar nuclear power generating stations, or 100 times the total power that we're generating in the US and 10 times the entire world coming from the sun. And of course, it's this heat that drives a lot of the plate tectonics and dynamics of the Earth. And if you're a geologist and you want to know how this happened, the evolution of our planet early on, then this is really important. And so if you consider all the possible ways that heat could be generating, one is that these radioactive elements We know all the known isotopes. How much heat could they be really contributing? There's a few likely suspects. It's uranium, thorium, and potassium. The others have some reason that they don't quite line up as likely candidates. But these processes produce neutrinos in their decay. And at the same time that they're producing neutrinos, these neutrinos will be able to escape, and we can detect them. And by the way, these are dumping enormous amounts of energy to fuel a lot of the observations we make on the surface. And so there was a kiloton scale scintillating detector called CAMLAND. It was constructed in Japan, surrounded by 53 commercial nuclear reactors to do neutrino physics. But they realized that if they did a careful analysis, they could sort out what was contributing coming from the nuclear reactors and look at the excess neutrinos. And so in 2005, they published an observation quantifying how much of the budget, the power output, was coming from these radioactive decays. And it's about half. It's up of the total energy budget is coming from these. And so now you have these 3 detectors that are capable of such investigations. And if you think about all of these higher energy neutrinos that are being created in the atmosphere, the higher energy ones have a higher cross-section for interacting in the Earth. You need a little bit of a higher probability than some of these others. You can actually think about doing tomography of the Earth with neutrinos. So this is one of the future areas of investigation. Now I'm going to transition to closer to home. There are 3 quick experiments that I'll talk about. The first one is the one that drew me back into basic science. And it's at the Spallation neutron source. And so this facility was built to do material science via neutron scattering in lower energy neutrons. And so material science, biological sciences. And so to that endeavor, they have a linear accelerator that propels protons. And every 16 milliseconds, multiple pulses of these protons are accelerated and stored. This is the accelerator up there. There's a storage ring. And then every 16 milliseconds, these particles then are directed to that building. And in that building is a liquid mercury target. And so if you were to look at the face of it, it looks something like that. And so the protons are coming at that target and dumping. Right now, they're operating at 1.4 megawatts of power. That's how many protons and energy is being dumped. There's enough energy when that pulse hits that face that it creates an audible sound for the system. The protons hit the mercury, and the reason they built the machine is it just rips neutrons off. And then they use those neutrons to do science. In the same process of the proton hitting that mercury, it creates other particles called pions. Pions are just pairs of the ups and downs, the same ones that go into the proton and neutron. But they're not stable, so they decay within tens of nanoseconds and through a sequence. And you get 3 flavors of neutrinos. Okay? And these 3 flavors of neutrinos are about 10 times the energy of the neutrinos coming out of a reactor. And people normally go to the SNS, and that target is located at some central some central monolith, and they open shutters, and they direct those neutrons to people doing that other kind of science. It turns out this is a really bad place for us to do neutrino science. We got stuck in the basement. Basement works really good for us. We're out of people's way, and we have no backgrounds to compete with our neutrino signals. And so we went after a neutrino signal that is different than the one I previously described. In this case, the neutrino, via a quantum mechanical effect, it sees the nucleus as one big ball of weak charge. And doesn't liberate any energy. There's no change of particle types. which means that it's really hard to detect because you have this almost massless particle scattering off this very heavy nucleus. The nucleus doesn't budge much, but it does budge just enough to leave some signals that if you have a really carefully prepared detector, you can see. And so normally these are kiloton detectors. Here are two students installing a 14 kilogram crystal of run-of-the-mill sodium iodide. It's a standard radiation detection material that gives flashes of light when things interact. And in this process, the cool thing is because it's quantum mechanically coherent, the result of that is you end up with a probability of interaction that's 100 times greater than the other typical interactions. And so even though we've got this small detector, it's as though it's 100 times the size. And so last summer, we sort of churned through a little over a year's worth of data. We had to count for a year, by the way. And sure enough, we see an excess. So this is the, in time, the arrival time of signals in that detector relative to when we know those protons hit and are creating those neutrinos. And so over the course of 5-7 microseconds, we see these neutrinos being detected in time, and then this is sort of the pulse height, or the how much light was deposited from that energy transfer. And then the blue, the green. The green is then the prediction from the standard model. And so we made this first observation, and that we in August we got the September cover, and then Daniel Friedman had predicted this interaction over 43 years ago. And so now the idea is we've got this new tool to use for investigating lots of other areas of physics, more exotic interactions. We don't know that we have excluded all the possible interactions of neutrinos with matter. And there are some that are highly likely. We have a way of investigating whether if they can still contribute. We don't know exactly how the neutron is put together. We know where the protons are because they have charge, but since the neutrons don't have electric charge, it's a lot harder to figure out how they're distributed in the nucleus. But since this interaction is tied to the neutrons, then we can disentangle the shape of the neutrons from the shape of the protons. And then I talked about all these complicated things that go on in a core collapse supernova. None of those interactions have ever been measured. And so they're going off of calculated values. It turns out that the neutrinos produced at the SNS are matched in energy and characteristics such that the SNS is really the right place to do a systematic study of those. There's another experiment at the high flux isotope reactor. This is our 83 megawatt reactor that has some unique 85, has some unique characteristics. And so they built a dedicated high precision detector to put next to this one-of-a-kind nuclear reactor core. It's really compact. It's made of only highly enriched uranium. And the reason they've done this is because all kinds of neutrino experiments have been based off of the neutrinos in the spectra and the flavors, the energy coming from a commercial reactor where you've got a funny mix of uranium and plutonium. And it's right now not adding up. And one of the possibilities is that there's an extra neutrino that we haven't discovered yet. And it would be a very different nature. And so this experiment in the coming year will be tackling that. There's another open question that's being addressed by a group at Oak Ridge, and that's to consider whether neutrinos could be their own antiparticle. Okay? If they're their own antiparticle, then it could explain why matter won out over antimatter. There is an isotope of germanium that wants to decay via that process we described, only it only wants to do it if he's got a buddy. So it's kind of like when before you jump into the river off the bluff, you're more likely to do it if somebody's standing there with you, jumping along with you, right? So these things go in pairs, and because they go in pairs, right now they produce neutrinos, and just like before, some of the energy is taken by neutrinos. If neutrinos are their own antiparticle, there's the possibility that there's a set of them where all the energy is dumped into these electrons coming out of the simultaneous decay. If they, right now, we know it's very rare. Like the lifetime of this process, 10 to the 25 years. There's an effort to build a ton scale of this germanium detector that would push that to 10 to the 27. And there's a huge effort in nuclear physics to pursue this. You know, like say a couple $100 million is what they're planning on spending in the next few years. One last one. I told you about the Relic Neutrinos. So many of you have heard of the cosmic microwave background. That's the light that suddenly was able to go free streaming in the early stages of the development of the Big Bang when the plasma, with electrons detached from atoms, would gobble up the light, redistribute it. When atoms were formed, it became neutral. The photons could transmit. And we still see that flash in the sky. And not only do we see that light, because it's moving away from us, is now shifted to microwave frequencies. But if you look at the sky, it's blotchy. It's not even. And if you look at models of the Big Bang, they should be able to describe that blotchiness. And here are data that have been recorded by 5 different experiments, and then the model that goes through those points. It's one of the best confirmations of something so far away, so remote from our own experience. And what an exquisite agreement. There's an analog to neutrinos the same way, but it's even farther back. This was a couple of 100,000 years after the Big Bang. The neutrinos decoupled 1 second after the Big Bang. And there are plans, they're still being explored to measure this contribution of neutrinos by capturing on something like tritium and doing a very careful measurement. So we may be able to tie and look all the way back to 1 second after the Big Bang in such a similarly exquisite way. Okay, so thank you for all of that, for your time and attention. I hope I've convinced you that neutrinos are these extraordinary particles that really do connect the universe at these vastly different scales, and that understanding their properties, while it's is a fundamental interest, but also that those properties make them uniquely equipped to use as a tool for all kinds of great science. And thanks to Wolfgang Pauli, and neutrinos are always a cause for celebration. Thank you.